Good morning, students. I hope everyone's doing well. Today, we're going to continue our work in Chapter 6 to investigate triangles. First, we're going to start out with a right triangle approach and not really say anything about what we've been doing. And then later, we will connect what we've done with the unit circle with the right triangles and see that our definitions for the trig functions will actually be equivalent. So this is probably what you've been waiting for, because I would suggest or say that possibly when you did your work in trig before, there was more emphasis on the triangles. So this should make everybody happy. Remember, for next week, we will have our third test. And so by the end of the week, I will post an announcement that will just basically guide you through the window of time for that. It'll be similar to the previous test. And of course, whatever we cover through this week will be fair game for the test. Remember, this test is just solely devoted to trigonometry. That's basically how I wanted to set it up so you wouldn't have any trig on the last test. So hopefully that made the last test a little less stressful. But what we want to do today is, like I say, go ahead and look at the right triangle. So let me share my screen. Now, like I said before, I'm not really going to make much of an attempt to connect things right away. I don't want you to think that, okay, well, I need to see the connection right away. And if I don't, I'm lost. I just want to propose a different way of looking at triangles as they suggest possible definitions for the trig function. So we're going to start out with that as a completely separate idea. So let's do this. Let's just draw our generic right triangle. And we have the abstract concept of an angle now that we produced with the unit circle and its comparison to the actual arc length. That is the arc that the angle subtends. And so we're just going to specify this particular acute angle to be theta. So remember, with a right triangle, you have a 90-degree angle or an angle of pi/2 radians and two acute angles. Now, what we want to do is characterize the sides of the triangle relative to this angle theta. So I'm going to use some abbreviations, and then I'll tell you what they mean. The side opposite of theta, we're going to call OPP. And opposite will just, OPP will just correspond to opposite for opposite side. Lots of abbreviations, but hopefully simple ones. Now, the side that will be adjacent to the angle theta will abbreviate ADJ. So ADJ will correspond to the word adjacent, to the side, so to speak, opposite to the side. And then, of course, the side opposite the right angle has a name that we all know from high school geometry. That's called the hypotenuse. So we'll just do HYP for that. So what I'm going to propose here will seem a little bit odd at first, but as we work through this and see, compare this to the unit circle, we're going to see that our definitions are actually consistent, though they may seem a little silly right now. So we're going to define, keeping in mind what we've already done, define 6 trigonometric functions. And we're going to keep in mind the idea of how they are related based on what we did with the unit circle. So they'll be, little tidbits of reminders of what we've already done. So that'll probably let the cat out of the bag, so to speak. So what we're going to do is we're going to define cosine theta. We're going to use the same abbreviations, cos for cosine theta, and we're going to define that to be, now, again, let me just specify because we're lazy. The ADG, not only does it specify the adjacent side, but we're going to make it have a double meaning. It will also specify the length of this side. So we don't want to have the luxury of having two labels. So this will correspond to the length. It also labels the side. Opposite will correspond to the length of the opposite side, and HYP, hypotenuse, will correspond to the length of the hypotenuse. Again, that's a double meaning, and we do it all the time, but I want to make sure that you understand that. So we're going to define the cosine to be the length of the adjacent side divided by the length of the hypotenuse. And then the sine theta, we're going to define the length of the opposite side divided by the length of the hypotenuse. Now, I'm not crazy. I'll show you that these actually turn out to be very good definitions. Now, what we want to do is remind ourselves of what we've done before. We're not really reinventing the wheel for the other four. We're just going to go ahead and say that secant theta to be, if we have any hope of showing the equivalence, we've got to start doing things that we did in the previous interpretation. So secant theta, we're going to define to basically be the reciprocal of cosine, the hypotenuse length over the adjacent. So this would be a wise move if we're thinking we want to show equivalence. Same for cosecant. It would make sense that we would define the cosecant as the length of the hypotenuse over the opposite. And then we'll just keep doing the same thing. We'll say tangent theta, thinking of how we did this in the unit circle, we're going to think of the y coordinate divided by the x coordinate, or the sine divided by the cosine. Well, when we do that, let's just write it down. We'll say opposite over hypotenuse divided by adjacent over hypotenuse. Now, of course, you see the hypotenuse lengths will absorb when we invert and multiply to just give us opposite over adjacent. So these absorb when you invert and multiply. So again, we're thinking, all right, well, that's going to be consistent, hopefully keeping our fingers crossed. And then we're thinking, okay, well, cotangent, we won't work so hard this time. We'll just define it to be the reciprocal of the tangent, which would be adjacent over opposite. Now, the tangent gets a lot of use. The sine and cosine get lots of use. So the idea is we'll probably spend more time with those three, but it's not going to preclude the others. It's kind of like with the inverse trig functions. We probably spend more time with inverse tangent, inverse sine, and inverse secant, even though the inverse cosine is defined and the inverse cotangent and the inverse cosecant. It just depends how the calculus works out. And again, we tend to gravitate towards trig functions that we know better or that we can actually get used to using, and we don't want to venture away from it so much. Now, when we think about these definitions, at least at this point, we're going to be focusing on lengths of the sides of the triangle as opposed to the angles, which will come later in the chapter. So let's just look at a simple example, and then we'll talk about some special triangles. So here's an example. We're going to draw a right triangle. This is like a Webisine problem. And we have a right angle, and then we have an acute angle theta here. And we're given that the hypotenuse has length 7 and the side opposite theta has length 6. So one thing that we know that we have with right triangles like we have with the unit circle are the Pythagorean identities, namely the Pythagorean theorem here. So for instance, this side here we call the adjacent. So we know that the adjacent, we'll just be lazy and use the labels we already have instead of making up new labels, just extra stuff that we don't need to clutter our work. So we'll say adjacent squared will be hypotenuse squared minus opposite squared. So this will be a, well, we can use, let's just use a difference of 2 squares. Let me show you another trick with factoring. So we'll have 7 minus 6 times 7 plus 6. That's just a difference of 2 squares, right? So you can multiply it out, or if the numbers are horrible, you can, but the numbers are easy here. So that'll just be a 1 times a 13, which is 13. So of course, now we will select the positive. Remember, with the square root property, we always get plus and minus, but we're looking for a length, so we select the positive. This is like doing the trig problems. And again, with this new interpretation, all those sign conventions will not change. None of that's going to change for us. All the stuff we've been doing, reference angle, reference number, they're all going to be the same. So we don't have to relearn anything. This part right here is really the new stuff. And I don't think it's that tough because I bet you've seen it before. But even if you haven't, it's very user friendly. So if we select the positive, this will imply that the adjacent side is the principal square root of 13. So now we could go over here and just add that. So I wrote this in red so we can see that we were given 7 and 6, and we could easily determine the adjacent side, and when I say adjacent side, it's length. So now we can go ahead and write down all the trig functions for this triangle. So cosine theta will be adjacent over hypotenuse. We'll write it down for sine and cosine, and then we can just do the traditional arithmetic details to get the other 4 without having to write all of these down. So adjacent over hypotenuse will be square root of 13 over 7. Now, another thing, again, when we move through this, like I said before, let's go ahead and write down the definition for sine theta, which should be opposite over hypotenuse. So that will be 6 over 7. And of course, you're thinking, well, you know, we haven't verified anything, but what you're seeing here is that with this definition, the Pythagorean theorem, which basically is the arithmetic behind the unit circle, it still preserves the values of the sine and cosine. That is, with this type of interpretation, there, at least all the values here will be positive because we haven't made our connection with the unit circle. But we've got all these positive values, and we see that they're between 0 and 1. We're never going to get anything bigger than 1 because of the Pythagorean theorem. So at least that part is consistent, and that's a good thing. So now let's go ahead and do tangent theta. Let me just write down what it is. Opposite, I said I wouldn't, but I'll do it anyway, over adjacent. So this will be basically sine over cosine if you want, or you can say, well, I'm not going to do that. I'm just going to do opposite over adjacent, which is 6 over square root 13. And you don't need to rationalize. Webasine doesn't care. That's fine. And then cotangent theta, we can just write this as adjacent over opposite, or just take the reciprocal of this. That we can do readily. So we're gonna make sure that that's the same as we did before. And then of course secant theta will just be hypotenuse over adjacent, that is the reciprocal of this. So we'll have 7 over 13, square root 13. And then lastly, cosecant will be hypotenuse over opposite, or the reciprocal here, 7 over 6. And of course, we see that these make sense. Again, we know that the secant, at least for the positive values, will be 1 or greater. And these are clearly adhering to that restriction. And then, of course, tangent and cotangent, they can have any values. Their values run from negative infinity to infinity. So we're covered here. So again, you know, that you could do like a little history paper and look at the history of trigonometry and see which portions came first. I mean, I don't know if it's known exactly. I mean, it just depends on when cultures decided to utilize these concepts, and they may have been used many years before things were formally written down. The idea is kind of like logarithms and Napier. I mean, such an ingenious invention has made our lives easier. But again, it's like, you know, which came first, the chicken or the egg? We're like, you know, well, which one did everyone use the most of? Did they focus on the triangles or the circle, or did they focus on, well, maybe not infinite series, because that had to wait for the calculus. So there are all kinds of things that you could discuss here in terms of a historical perspective. Now, let's look at, I just want to take the time here to talk about some special triangles, since you did take high school geometry. So, well, you know what, many years ago, or maybe it wasn't that long ago, high school geometry is a staple. So I just want to write down some special triangles, and then we'll do some examples. So the first triangle is the one that you see a lot, the 45, 45, 90. So this makes what we call an isosceles triangle. Two of the sides are congruent, or the legs are congruent. So we'll just draw our isosceles triangle. So again, we don't want to write forever. So I'm just going to say here, we're going to do S for side. And of course, S for side here because it's isosceles. And then we'll do H for hypotenuse, again, because we're lazy. Now, again, we have a 45-degree angle here. And obviously, we have 45 here, just using the angle sum of a Euclidean triangle, which is 180 degrees. So now we're thinking, okay, well, what's the relationship between the sides, the legs, so to speak, and the hypotenuse? Well, we can just use the Pythagorean theorem. So this implies that, and again, we don't even have to think about trigonometry yet. We can say, okay, well, S squared plus S squared equals H squared. So that'll give us a 2S squared equals H squared. So we can divide by 2 or just leave it alone. So we're going to select the positive here. So select positive radical, because these are sides, select positive. And this will give us H equals the square root of 2 times the absolute value of S. Again, when we think about this and we think about what we're doing as far as taking square roots and things, like we did with the result over here. Notice we had the square root of 13, but here we've got the square root of a square, which is the absolute value of S, but by definition, S is non-negative. So this is just the square root of 2 times S. So what we see here is that the hypotenuse will always be the square root of 2 times the side length, or just S. Equivalently, we could just say, we could divide and just say the shorter side is just H over the square root of 2. Now, of course, you don't have to memorize any of this. If we think about how things work out, and we already know about how to compute sine and cosine of 45 degrees, that'll be 1 over root 2. We'll get the same thing. So none of that we're throwing away. We're going to think of what we've done, especially with our trigonometry so far, that we're preserving all of that. But we're like, do we even have any right to do that at this point? We're going to assume we can, but then we're going to show that it actually does make sense. Now, the second triangle is the 30, 60, 90. Again, this is another important triangle that you see in high school geometry. And what we want to do in this case is start with an equilateral triangle. So let's have a triangle that has 3 sides of equal length. So 3 sides are congruent. So here, again, we've got 60 degrees, 60 degrees, 60 degrees by the angle sum. They're all congruent. So what we want to do first, we'll just call all of the sides by S. And then to make this work, we're going to drop a perpendicular bisector. So we'll just call the height of the triangle H. Over there, we were thinking H was hypotenuse, but I guess it doesn't matter. We'll just use H. And so now we're thinking, well, what are we doing here? Well, first, when we drop the perpendicular bisector, let me just go ahead and let me move this over. This has length S. I'll just go ahead and write it down here to get it out of the way. But then, of course, if we drop the perpendicular bisector, this length here is just S over 2. So now we're thinking, okay, well, what do we want to do now? Okay, so if all of these are side S, what can we do to make this work? Now, here's a labeling problem. This is not, let's not call this H. Let me do a little better than this. Let's call it L, because if we look here, this side here, when we bisect this angle, this is going to be 30 degrees. This is 60 degrees. And so we're going to have the shorter side opposite the smaller angle. And we usually refer to the side opposite the larger angle as L. So let me call this L for longer side. Just, you know, I think that'll be better. That's a little bit confusing to call it H, even though H is fine for height of the triangle. So now what we can see is that we can utilize the Pythagorean theorem. So now notice this implies, and of course the hypotenuse just has length S. So we have S squared plus S over 2 squared. Oh, sorry. That's the hypotenuse. Plus L squared. So now the hypotenuse squared equals the sum of the squares of the legs. So S over 2 squared plus L squared. So we have S squared equals S squared over 4 plus L squared. And now we can solve for L squared. We'll just write the L squared on the left. And basically 1/4 from 1 will be 3/4. So we get 3 S squared over 4. And now again, select positive, again, because L is a non-negative quantity. So this implies that L equals the square root of 3 times the absolute value of S divided by 2. And of course, S being non-negative, its absolute value will just be S. So when we look at this, we think, okay, well, we've got this side of the triangle, which we call, in this case, S. And then we want to say, okay, well, how can we make these problems a little bit more user friendly now? Because we've got everything written correctly. So now what we want to do is now think about what I've done here, and then think of this as the H, as the hypotenuse. So now our formulas will look like this. So they'll look nice and pretty like that. So formulas. This is indeed the hypotenuse S. So we're going to say that L, in this case, is the square root of 3 times H over 2. Again, we'll say L corresponds to longer side, and H corresponds to hypotenuse. And then now, of course, we already have the shorter side in this particular case, which we can again think, okay, well, how are we going to call shorter side? So we're going to change everything up. We're going to say S will correspond to shorter side. Maybe I should have just started with a different letter altogether. So then we'll say S, shorter side, will just be half the hypotenuse. Now, when we look at this and we say, okay, well, what does that mean? That means now that if we made a substitution here, the longer side is just the square root of 3 times the shorter side. So now with these labels for a 30, 60, 90 triangle, now we can do it. Let me just draw here. That was our computation. So let's just draw the 30, 60, 90. So here's the 60. Here's the 30. And so this will be the longer side. This will be the shorter side. And this is the hypotenuse. And so now we see that the shorter side is half the length of the hypotenuse. The longer side is the square root of 3 times the shorter side. And then, of course, this one's kind of useless. If you know these, you're done. The longer side is just square root of 3 over 2 times the hypotenuse. But you see, that's just a simple substitution there. So that one's really probably not as useful. But we see now that just like with the 45, 45, 90, let me just go ahead and write this under here so you can include this in your notes. We don't really say, we don't have really special names here. We just say H, where H corresponds to hypotenuse. We'll do it the same way as we did the one down here. And S will just be the side. Since they're the same, we don't differentiate between them. Right there. And you can include your 45 degrees. So this will be like the tallying, so to speak. Once we do our calculations and do all of that, then we make the labeling more user-friendly. Again, again, L for longer side, S for shorter side, and H for hypotenuse. So these are just nice little formulas that you can get from your high school geometry, just basically knowing the Pythagorean theorem. So we could have just started all of our work this way and forgotten the unit circle, but that would have been hideous when we tried to do graphs and talk about inverse trig functions. But we're going to see that this is going to be so useful. So now we've got some ways to think about 30, 60, 90, and 45, 45, 90 triangles. Now, I want to look at an example where we just do a computation. That is, let's say that we've got something like this, just a nice little diagram that has 30, 60, 90 triangles in it. So we're going to start with a side length. We're going to have basically 3 triangles. So we've got this piece, this side, and the hypotenuse. And we're going to have a 60-degree angle here. And the length here will be 70 units. And then we're going to extend and draw another 30, 60, 90. So notice up here, this is going to be a right angle here. So that'll be 30 degrees. And of course, this will be our 30 degree. And we'll have our 60 degree. So this is an interesting setup. We've got right angles here, a right angle there, kind of an interesting little diagram. And so that's all we're given. And then we have a label. This is a label that WebAssign gives you. So we're going to use, we can kind of look at this way using the trig functions as we thought about them with the unit circle, or you can think 30, 60, 90. Now, obviously, when you look at this particular problem, you're thinking, excuse me, what Professor Wine is going to ask us to do? Well, I want you to compute X, and that is the length X as a length. So now you're thinking, well, we've got these 2 triangles that are smaller and then this one big one. Maybe I could make this a little bit easier by breaking this down into 2 pieces. So what we're going to do is we're going to chop it up. We're going to look at this side length as A from here to here. And then from the second triangle here, we're going to think of this as B, just giving it a label. So you could think of this maybe as triangle 1 and this triangle 2, if you like. So now when you look at this and you say, okay, well, this is a 30, 60, 90 triangle, and here's the shorter side, and there's the longer side. Now, when we look here, the shorter side is just the longer side divided by the square root of 3. So we can use this formula. So use 30, 60, 90. We'll do it 2 ways. So by 30, 60, 90, we see that A will be 70 over the square root of 3. Because we know with the 30, 60, 90 that the longer side is just the square root of 3 times the shorter side. And then we know that that's all we're really going to need. And we know that the shorter side is just twice the hypotenuse length. So if I want the shorter side given the longer, I just divide the longer side here by square root of 3. Now look here. Let's see, what else do we have? How can we get B? Well, again, notice it's the same. It's basically looking to be the same thing. Here, we've got the longer side here, and we've got the shorter side here. So the shorter side, this is being the longer side. So now we'll use this directly. So B, again, in this case, which is the longer side, will be the square root of 3 times 70. So just use this directly. Times the 70. And then, of course, I'll write it so it looks a little bit better, 70 times square root of 3. So that's just using this formula here. Same formula, one we multiply, one we divide. So now we're thinking, well, we're done. That was easy, just using 30, 60, 90. So this implies X equals A plus B. So this will be 70 divided by square root 3 plus 70 times the square root of 3. And then, of course, if you wanted to, you could factor this. I mean, why not? I don't think it really matters at this point, but we could factor the 70 over root 3 from both. So if you want to do this, first do this so it's easy. 70 divided by root 3. Now multiply and divide by root 3. So this will be a 70. Again, if we multiply here by root 3, that'll be a 3. And then a root 3 here. So now divide or factor the 70 over root 3. Many ways to do this. And this will be a 1 plus 1 over root 3. And you're thinking, well, that doesn't look, that beautiful. Maybe we could have just taken out the square root of 3, but either way is fine. And so now, if you like, 70 over root 3 let's just say this, and I'll finish this, but you're thinking, is this even prettier? This is kind of ugly, but let me finish it. That equals this. And then you're thinking, well, we could have made that look a little bit prettier. Now that's factoring it this way. Let's try it another way, just as some practice. So we have 70 over root 3, just to make it look a little bit neater. So now this time, I'm just going to take out the 70 times the root 3. Just take that out. Now I've got to pay for this by basically saying that I have, when I actually do that, I've got to multiply this by what? Or divide this by square root of 3. So that's going to be 1 divided by the square root of 3 squared. So that'll be 1 plus 1/3. So now when you multiply back through, you'll get root 3 over 3, which is 1 over root 3. So this is actually nicer because we get rid of the fractions. So now we get 70 root 3, and we have a 3. So this is going to be what? A 4 plus a 1. So this will give us 4/3 times 70 times root 3. So that'll be 280 root 3 over 3. And that looks a whole lot better. That's kind of unfortunate looking. I mean, we can revive it, it would be okay, but that's a little bit unfortunate looking. It's equivalent to this, but this looks nicer. So notice here, we just looked at this by factoring 70 over root 3, but then of course that still leaves the radical in the denominator. And notice here, let's see here. Let's see. Yeah, everything looks good. Let me just make sure that this is equivalent. So 70 over root 3, and then we've got, oh, sorry about that. So notice here, when we make this factorization, I've got an error here. I know you all saw that. You're just being kind. We get the same thing. That'll just be the 3 here. So it actually was nice. You got 2 calculations that weren't all that together necessary. So here, when we factor the 70 over root 3, that just leaves a 3. So that gives us the 4. And so now we get 280 over the square root of 3. And if you rationalize it, you get 280 root 3 over 3. So these are equivalent. So actually, this was actually okay. This was good. But see, that's what I like to do here. I like to just work through the arithmetic so you can see what symbolic computation is all about. Because when you look at this and you say the factoring is going on, it's like, wait a minute, these should look alike. And so when I factor here, I have to remember to remove everything. You remove all of this, leaving a 1, then you remove all of this, leaving the 3 behind. So these are equivalent. And now, of course, if WebAssign asks you to approximate, you can. And again, this is the exact response. Now, remember, and I've said this a million times, mathematics requires the exact answer. If an approximation is requested, then do it. But don't push that on the problem. A lot of you will say, oh, well, I'm just going to use 3.14. No, you use the symbol for pi. If the problem says approximate to a certain number of decimals, you work it out exactly. No estimations, and then you do the approximation using your Google calculator. Otherwise, you ruin the problem. It's better to work through the problem and check your work like I've done here to say, well, you might be working this problem and say you factored it this way, or say you factored it this way. The result should be an equivalent answer. And so what's nice about this is by doing it a second way here, I noticed the arithmetic mistake here. So that's the beauty of doing symbolic calculation. You can always check your work. If you're punching on a calculator, you have no idea what you're doing. And that's what I'm trying to avoid here. That is, use the calculator as a tool, not as a substitute for your brain. So this is a nice calculation. Now, the beauty of it here is that we can use the tangent and the sines and the sine of 60 degrees or tangent of 60 degrees or anything like that. But I wanted to show you how you could actually do a problem using the construct that we have here with the 30, 60, 90 and the 45, 45, 90 here. So this is something that you should be able to do. And if you ever tutor someone in geometry, you can utilize this argument to help them with that. Now, let's try another one. These are fun problems. This is like what you did in high school math. So we're remembering our roots. Now, the next example, we're going to use some of our knowledge of opposites, adjacents, things like that. So we're going to actually use the construct that I gave you at the beginning of the lecture. So here we have an example. That is, we have a lighthouse, and I'm here, not very artistic here. I'll just say, here's my lighthouse. And we have, in this particular case, let's see, what was given in this particular case. We've got a lighthouse that is 180 feet in height. And from the lighthouse, you've got a boat right here. Say you're in a boat by the lighthouse. And you're given, we construct the horizontal at the top of the lighthouse. You're given that the angle of depression to the boat where you're paddling, angle of depression to the boat is 23 degrees. So we'll say angle of depression is 23 degrees. And so, of course, we have a right angle here. So we have to make that assumption to do the problem. And then we're asked, compute the boat distance from the lighthouse. Okay, So now if you like, you could just notate this distance here as D. Now notice if we look here, we've got complementary angles. So 90 degrees minus 23 degrees, that'll give us a 7 and then an 8. So we get 67 degrees. So here, I'll use another color. We have a 67-degree angle. Now, of course, you don't have to do the problem with this triangle. You can choose. You can say, well, I'll just go ahead and use this one. I can use the right angle here. It doesn't matter. You know, and D is also parallel here. I've got a D up there. So either way is good. And then, of course, I can move the 180 over here if you like. So you have your choice of triangles. So now we can look at this and say, well, okay, well, let's just use the one since we bothered to compute the 67 degrees here. And so we think, okay, well, the D, here's our right angle, and the D is opposite of the angle 67 degrees, and the 180 is the side that's adjacent. So we're thinking opposite over adjacent, so we can use tangent. So use tangent. I mean, that's one thing to use, it's easy. So we can think of this as opposite adjacent. So then we have tangent of 67 degrees will equal the opposite, which is the unknown side D, divided by 180. If and only if D equals 180 times tangent of 67 degrees. Now, of course, with distance, it doesn't matter in this case. We can go ahead and convert, for instance, depending on how we want to do this particular problem. If we were using our Google calculator, we could actually convert the 67 degrees to radians, if you like, or we can just leave it alone and make sure we're in the degree mode. So this would be the exact distance. But in this particular case, WebAssign says round to nearest foot, round to nearest foot. So again, WebAssign said that not really exact answer is good, but now I want you've got a client that needs rounding to the nearest foot. So what we can do, let me share my Google calculator. Let's see, let me make sure that WebAssign, not WebAssign, but that Zoom can see it. Get rid of all the extra windows that Zoom opens up for me. So let's see here. Okay, you can see it. Let's see, Google Calculator. Let me get rid of that. Now see if we can see it. Now it sees it, good. So here we go. So we can go ahead and transfer our calculator into the degree mode if you like. So we'll have 180 times tangent of 67 degrees. Again, we're in the degree mode. And this will give us approximately 424.0534. And then, of course, WebAssign says to round to the nearest foot. So this will be 424 feet. So again, when we do our calculations, we do our calculations exactly. And if WebAssign asks for an approximation, then we approximate the exact response. So again, you have your choice of triangles. And this is where you can see that this second interpretation that we're keeping our fingers crossed is valid is turning out to be very useful because again, we're dealing with ratios of sides of triangles. And so this is a much nicer and more convenient interpretation that we actually have on the unit circle. We just haven't seen it yet because we haven't looked for it. Now let's look at another example that's similar to this. So this is kind of fun. This brings you back to your days when you were in high school. And it's kind of fun. Now let's look at a similar example where we can use our trig functions with angles that aren't very pretty, like the 45, 45, 90, 30, 60, 90, like we saw in the problem previous to the last one. So here's another example. So in this case, we've got one big right triangle that's subdivided. So here's what we have. We've got, I'll draw the picture. This is a word problem. So basically, you have an observer, maybe a surveyor, and when they're at this point to the left of the mountain, they notice an angle of elevation of 32 degrees. So at this point, 32-degree angle of elevation from the horizontal. And then they notice if they move their position closer to the mountain by 1,000, in this case, this is feet. So they change their position and they move to this position closer to the mountain by 1,000 feet. And then they measure the angle of elevation and they find it to be 35 degrees. So if you're a surveyor, you're going to really like your right triangles, especially, you know, when you're trying to solve problems of this nature. And then the question is here is compute the height of the mountain. So this is the mountain, this side, that's the mountain, that's our mathematics. Compute the height of the mountain. So what we can do is say, okay, well, we'll just call that h for height. This time we're using h, the height, not hypotenuse. And then, of course, we've got two triangles here. We've got a big right triangle and a smaller one. So we're going to need to know this side to do some computation. So we're going to make a designation. That is, we start with everything in black. That is, we have two angles of elevation. We have this distance, and we're asked to estimate or compute the height of the mountain. Now, the idea here is that if you like, we can say triangle one here, meaning not the obtuse triangle, but the larger right triangle. So we'll say one corresponds to larger right triangle, and two will just be, in this case, the other right triangle. And we'll just put that as 2 right there. So again, the 1 is all the way around, the larger right triangle, and then the 2 is just this one. And so we're thinking we need to find h, so we can find equations that will involve the h and the x and then solve for h. So with the first triangle, and notice, and this is what makes this problem fairly straightforward. We've got really nice angles here, and then our friend, when we compare, if we say this larger triangle, we've got the opposite side and we have the adjacent side relative to the angle 32 degrees. And so we're like, yay, we can use tangent. So again, use tangent. Tangent is our friend. So we can say tangent of 32 degrees. Again, we don't use special triangles here. Tangent of 32 degrees will be the opposite side. I'll go ahead and write this out. Opposite side over adjacent. So that will be h divided by 1,000 plus x, or x plus 1,000. So I'll put this in a box. So we've got tangent 32 degrees equals h divided by x plus 1,000. So that gives us an equation. And then for the second triangle, the smaller one we have here, we'll use tangent again. We'll say tangent of 35 degrees. Again, the Google calculator uses the calculus to approximate the trig functions. And then of course it'll do the conversion automatically if we switch to degree mode, or we can just do the conversion ourselves and convert to radian mode and not have to change. So you always have that option when you're working with angles or radians. So we have h over x. So now when you look at this and you think, okay, well, what does this tell us? We're thinking, well, you know, we've got h is equal to x times 35 degrees. Or tangent of 35 degrees. So there are many ways to do this problem. So now when you look at this, you're thinking, well, I could set the h is equal and solve for x, and then substitute here to get h. That would be one way to do it. I mean, there are a huge number of ways. Just by looking at this, there's many ways to do this. So for instance here, if we cross multiply, we see that h is x times the tangent of 35 degrees. And here we could also solve for h. So let's do it that way just for fun. It doesn't matter. I mean, how you solve it is completely up to you. So this h equals x plus 1,000 times tangent of 32 degrees. So h equals x times tangent of 32 degrees. I'm just putting the degrees so you remember it's degrees and not radians, plus 1,000 times tangent of 32 degrees. So that's even better. So now we can solve for x. So we'll call this, we'll just basically, again, we'll just call this 2, and we'll call this 1 since they come from those respective triangles. So equate 1 and 2, solve for x. And then once we have x, we can substitute here and get h. That's just one way to do it. Or we could just solve for h exactly, but I'm thinking this might be simpler for you. So now we get x times tangent of 35 degrees equals x times tangent of 32 degrees plus 1,000 tangent 32 degrees. So we can solve for x, get everything on one side. So x will be tangent of 35 degrees. And then of course, when we subtract this, take this over, that'll be a minus tangent of 32 degrees equals 1,000 times tangent of 32 degrees. So these aren't equal, they're clearly different. The tangent is 1 to 1, at least on this branch. So x will be 1,000 tangent 32 degrees divided by tangent 35 degrees minus tangent of 32 degrees. Okay, so that's what that is. And so now we're done. X is this and H is just tangent of 35 degrees times X. So this implies that H equals, well, we'll just go ahead and multiply it out, X times tangent of 35. So that'll be 1,000 tangent 32 degrees times tangent. I put a little dot there so you see, I don't need to, but I'll just to make an emphasis, 35 degrees divided by tangent 35 degrees minus tangent 32 degrees. So this is exact because it said to compute the height of the mountain. So this is the exact computation. Let me refocus a little. So this is one way to do it. I mean, when you draw these problems, and I look in your WebAssign and I pick some examples to work out in lecture. And as I look at them, I'm like, okay, here's a way to do it, but this is certainly not the only way to do it. But this is exact here, and that's how I have taught you. So now we can go to Google and we can get an answer, at least an approximation. This is a correct answer. I've told some of my students, I said I may change some of these problems where you actually have to type this like you did with the solving the log equations and then do the approximation, just so I could see that you're actually doing this. I may change that in the future. So let's do stop share, and we'll go to Google, our friend Google. And so let's go ahead and use, we need to get all of this. We'll need just to use parentheses downstairs. So we're going to say, I'll put this together. And okay, go over here and let's make sure we're in degrees, DEG. So we've got 1,000 times tangent, TAN, tangent 32 degrees, times tangent 35 degrees. Good old Google. Close, and we want to divide by the difference, use your parentheses, tangent 35 degrees minus tangent of 32 degrees. And this gives us 5,807.6554. And in this problem, let's see what it say, round to the nearest foot. So this will give us 5,808 feet. So this is, I mean, it's weird, but Professor Ron is probably the most consistent professor you will ever have, because I work problems the same way. I never vary. Everything's exact. And then when you see how I do these problems, and you see that my methods help you to check your work, then it's going to transform how you do math. Because now again, regardless of how you looked at these equations, we do a lot of this in calculus where we have the same expressions representing or different expressions representing the same variable. So we equate the expressions. That way we can solve for X, and then we have a very simple equation. Of course, I could have used this one, but that's too complicated. This one's easy. And so I get my exact expression for X and then multiply by tangent of 35 to get H. And here's exact, and then here's my approximation. So the nice thing about the triangles we're seeing here is that by expressing our tangent function as a ratio of the opposite side to the adjacent side of a triangle, right triangle, gives us a way to solve this problem that really, for instance, if we were just looking at the unit circle and the radian measure, we might not be as successful, because we see the radian measure helps us with the understanding of the unit circle from a standpoint of identities, even and odd, inverse trig, graphs. That was the perfect scenario for interpreting those concepts. Triangles would have been a disaster. But now that we look at a problem like this, the triangles are what save us, so to speak. So what we're going to find is that when we merge the two, we've got the best of both worlds, and we're like, yeah, this is what we want to do. We want a understanding of trigonometry that we can apply a dual purpose, so to speak, that we can apply as we need to solve problems. So again, this is a nice example of where the triangles turn out to be very useful. Again, when we think about this problem here, we didn't allude to the triangles, but I mean to the ratios. You easily could have done it that way, but I thought, well, since these were nice triangles, we'll just use the formulas that we've developed. So at least if you have a nice triangle, you can just go ahead and think of it this way, or do it with the ratios. I think this was just nice because we just got a little practice doing some factoring, which is always good. Never a bad thing to factor and to manipulate things. That, as a mathematician, I do it all the time in the work that I do. When I sit down to read, I sit down with, like I'm teaching you all, with pencil and paper, and it's arduous, but that's the only way to study mathematics. Now, well, okay, well, good for us. Now, what does this make any sense in terms of what we've been thinking about with I don't know, what was the first thing I said? I said I'm going to go ahead and define some definitions and not tell you about why I'm doing it. What I want to do now is show you that what we've been doing actually is good. So this will be 6.3. And everything we've done before, we'll pretty much do again the same way. So this goes really quick once I show you the equivalence. So this will be trig functions of angles. Because we've already been doing that. In this last example that we set up, or the last section, I said we're going to assume that we can take tangents of angles and approximate them and do like we've been doing with the unit circle. But why is that possible? Why can we do this and be okay? Now here's what I want to do and give you some idea about how this is going to work. Now, for instance, we're going to take the unit circle. So I want you to draw a circle within a circle. Now, of course, the second circle can be larger or smaller. I'll just take a larger one so it's easier to see. So we just draw your axes. So we want to just make sure that what we're embarking on is actually good, that it's equivalent to the interpretation that we started with the unit circle, and that everything's okay. So let's do a unit circle. So draw a unit circle. And now just take, we'll say we're going to start with the unit circle, and then we're going to fix r bigger than 1. Okay, so we'll take a larger r, so something bigger than 1. So draw that. Of course, we could take a smaller one. It won't matter, smaller or larger. I'll just do the larger so it's easier for you to see. So So this is the inside one. We're going to just draw, and we're going to create an angle. It'll be in standard position, but it doesn't really matter. It just makes it a little bit easier because we have reference angles now and reference numbers. They're the same thing. They're computed the same. So we're going to just construct an abstract angle, call it theta. So this is going to be theta. And the first, that's going to be R1, the radius 1 for the unit circle. And then, of course, we'll have this distance here. And then for the bigger one, this is just going to be the radius R to this point. And it'll have a distance along the unit circle here. Now in each case, so for the first one, we're just going to call this point, we're going to call it XY, that we normally do on the unit circle. And then for this point here, we'll just call this P1, X1, Y1. And so in both cases, what we want to do is impose the right triangle. One here, drop the perpendicular right there, and then one here. Again, it doesn't matter where we draw an angle or where it is, you know, it doesn't matter. You can extend the sides of the angle, that is these chords from the center of the circle, indefinitely. It doesn't matter. And we saw how we can compare the arc length to the actual angle S equal R theta when theta is measured in radians. So now what we see here, just like we had before, we have a smaller right angle and a larger one that are similar. So we have two, so we're going to use the law of similar triangles. We have two similar right triangles. That is, they have the same angle here, right angle and theta, and so the third angle by 180-degree angle sum must be the same. So this angle here and this angle here, they're congruent. So these triangles are similar. So this means ratios of corresponding sides. This is a huge theorem in geometry, and it is not easy to prove. I've proven it before in a seminar, and I thought we should have done something easier. Ratios of corresponding sides are equal. That's a major result. We depend on this result. Trigonometry would not be consistent without the law of similar triangles. People like to try to prove this with the law of sines, but you can't. It's circular. Everybody wants a shortcut. Shortcuts are fine when they're consistent, but when your reasoning is circular, you can't assume what you want to prove in your argument. It's like we want to prove x equals 2, so we assume x equals 2. That's called circular reasoning. A very simple case of it, but I think you know what I mean. So now we're thinking, okay, well, let's just look at this. If we start with S1, or that is the circle here, so this is S1, and we'll just call the circle of radius R, we'll just call that SR. So when we start with S1, we have cosine of theta. That's just equal to X, right? But we can write that, excuse me, and if you want, this is X right here. Let me just go ahead and draw it in. This is X. and this distance here is y. Likewise, this distance here is x1, and the distance from here down to the y-axis or x-axis is y1 right there. So y, y1, x, x1. So cosine of x, by definition of the unit circle, trigonometric definition, is x, but that is also adjacent over hypotenuse, which is x over 1. But now that we see this by laws of similar triangles, the adjacent side here of the larger triangle of the hypotenuse is also equal to this. So this will be x1 over r. Those are equal by the law of similar triangles. So basically what we see here is that in both cases, we get adjacent over hypotenuse, regardless of the circle, regardless of the triangle. So what we see here is that with this type of reasoning power here, we're done. No matter what circle we use, it doesn't matter. The law of similar triangles will preserve the adjacent over hypotenuse. So this checks. So basically, if we define the cosine of theta to be the x coordinate of the terminal point on the unit circle, that's equivalent to the x over r for any circle that corresponds to that theta by constructing adjacent over hypotenuse. So then you're saying, oh, I get it. Now we're going to think about this as just the x1 over the r. We're always going to think of it that way and we'll be done. We'll think of adjacent over hypotenuse and not even worry about drawing two triangles. Now for sine, it's the same thing. So here's the S1 and here's the SR. So we'll start with S1. If we're on the unit circle, the terminal point that corresponds to theta, or the distance along the unit circle, is xy, and sine theta is defined to be y. But we can write that as opposite. That's the opposite side, in this case y, divided by the hypotenuse. But by laws of similar triangles, ratios of corresponding sides are equal, so the corresponding sides here will be y1 over r, that ratio, which again is opposite over hypotenuse. So it doesn't matter which circle we use, it doesn't matter which triangles we use, the ratios are equivalent. And so our interpretations are equivalent. And then of course, tangent, cotangent, secant, and cosecant were all defined using the same development that we use to define them for the unit circle. So we're done. All we have to do is verify for cosine and sine. So this implies the S1 interpretation, of the trig functions is equivalent to the right triangle interpretation. So, wow. So now we do this. We're happy. So there's the argument right there, and that's why this all now fits together. Law of similar triangles. So trigonometry is a geometric result if we start this way. Of course, if you think about it in terms of analysis, then it's kind of insane. So you're thinking, when we think about the trig functions here, now the inputs, instead of being the distances along the unit circle will just be the angles. And we can measure angles counterclockwise, and we can measure angles clockwise. So now the angle takes the place of the t value, and the thing is, everything is the same. So in the second interpretation, theta takes the place of t, and theta hat, which is a reference angle, is defined exactly like t bar, which is the reference number. No difference. Everything's the same. All arithmetic calculations are the same. Pythagorean identities, everything's the same. All we've done is just show that the Pythagorean theorem is really tying all of this together as long as we have the law of similar triangles. If we just had the Pythagorean theorem, we couldn't do this. We have to have the law of similar triangles to show the equivalence. And it's, again, the equality of the corresponding ratios. That's an amazing result. Again, the beauty of Euclidean geometry is that it allows us to stretch our wings, so to speak, and solve problems that would have been before just completely beyond us. Now, I want to look at some examples where we actually do some calculations. Now, like I say, in this section, anytime you see reference number or you compute trig values or anything, you do it exactly like you did in 6.1. You do it exactly, excuse me, 5.1, way back, 5.1, 5.2, back when you just started the unit circle. All of these problems are done the same way. You just, instead of drawing a t, you're drawing a theta, but now you can use the fact that you understand right triangles if that's going to help your calculations at all. Then now you have the luxury of the right triangle. So again, you can impose the right triangle if you want. And the reference numbers have to make sense. So remember, when triangle sides are non-negative, so when you start throwing in the negatives and positives, you've got to think about reference numbers so that the triangles make sense. That's the only little thorn in your side. So let's do some examples. There's a result here. Now that we have this triangle approach, we can now find the area of a triangle using trig. You know, what do we remember? Back in high school geometry, you proved that the area of the triangle is 1/2 the base of the triangle, length of the base times the height. Again, I'll just say in high school geometry, very important course, high school geometry, the area of a triangle is proven to be 1/2 base height. That's an elegant result. You should think about how you prove that. I can't reinvent everything for you, so you have to do some work on your own. You should investigate that. And so we can take this idea and utilize some trigonometry. So for instance, here's a little theorem. Consider a triangle with sides A and B and lots of ands. Consider a triangle with sides A and B and an included angle of theta. So basically, let me just draw a case one here. What that looks like. we'll have a triangle. We'll draw an acute triangle. So we have a triangle with side lengths A and B, and we have an included angle. So consider a triangle with sides A and B and an included angle theta, like here. So when we say we have an included angle, we're saying that basically we're looking at this as like a vertex, so to speak. That is, we have two sides and included angle, just like you did in high school geometry. So the same terminology is at work here. Then area of triangle, we can write this in terms of trigonometry, is 1/2 AB times the sine of the included angle. So you're thinking that's just 1/2 base times height. That's pretty much what it is. And you're like, oh, okay, well this makes the area of a triangle at least more user-friendly. Maybe I don't have a 30-60-90 or a 45-45-90 or an equilateral triangle, which is a nice triangle that I can do exactly. With the use of trigonometry, I can still write an exact answer for the area, but I might have to use my Google calculator to do a calculus approximation. So let's look at the cases here. Let's start with the acute triangle and drop the perpendicular. So if we're going to use the trigonometry, at least as we have it right now, we've got to have some right angle somewhere. Later on, we'll relax this a little bit with some other triangle theorems, even though they're kind of useless at times. That we still want to talk about them. So what I'll do here is we'll drop a perpendicular. So let me just kind of do that in red since we didn't start with that. And we'll call this length H for height. I know I'm using H for hypotenuse all kinds of ways. Just remember, as we start out with the problem, we will use some lettering, and then we may change it up a little bit to make it more user-friendly with letters as a summary of our results, just to make it look nicer so you could remember it. So don't be put out by that. Just know that that's the routine of doing mathematics. And that's probably what you encounter when you do your own problems. So when we look at this, we're thinking, okay, well, this is easy. I've got the height of the triangle, which I can define in terms of a ratio. So now we're thinking, okay, here's the base here, and I've got this right triangle that has hypotenuse H. So this implies that sine of theta, which is opposite over hypotenuse, again, opposite over hypotenuse will just be H over A. If and only if height, just cross multiply, is A times sine theta. That's why I did that long problem with the two triangles and the angles of elevations for the mountain, to get you used to doing this. And okay, so we're done. So then area is 1/2 base times height. The base is B. Again, we use the letter to denote the length. So we have 1/2 B times A sine theta. So just make it look pretty, 1/2 AB sine theta. Well, that was trivial. So what's the other case? So now you have a new formulation for computing the area of a triangle, okay? That's fine. And so now what's the other case? We have an obtuse triangle. So this is acute triangle, and this is obtuse. So what this is going to do for you is going to help make the unit circle less abstract, even though you must embrace the unit circle. This will give you more time to master it. So now let's look at an obtuse triangle. So that has an angle larger than pi/2 radians, or larger than 92 or 90 degrees. Something like this. So now, again, we'll have a theta, and we'll have, I guess I'll do it the same way I did this one. It doesn't matter. We'll just call this, do it the same way, have an A and a B. So A, B. So that's this side A, side B included angle. Then, of course, we've got to get a right angle, so we're going to extend the horizontal, basically extend the base. We have to extend the base to get the height of the triangle, so we drop the perpendicular. And call this H. Now when we look at this and we think about this particular setup here, this theta is in the second quadrant. So this is, we have to do some analysis here. So theta is in the second quadrant. And there's the reference angle right there. So this implies that theta hat will just be what? Pi minus theta. So when we look at that, that gives us the reference angle. So this right here is the reference angle. But again, remember, sine of theta, that's in the second quadrant, is y, that's positive. So this implies that sine of theta equals sine of theta hat. So that's really important. That's just using our unit circle, which I beat into your head, okay? So again, notice this is giving us the pi, or 180 degrees minus theta right here, the reference angle. So now we can say this implies that, okay, so we'll say sine of the reference angle is H, again, over the hypotenuse. Now, this is where I have to use the fact that, let me draw this. Let me kind of, the smaller triangle, let me call this one 1. This is the smaller right triangle. So 1 corresponds to the right triangle. I'm a little bit careless there, and I don't want to start writing and saying when it doesn't make sense. So now notice we've got this right angle here, this right triangle right here. So now sine of theta hat will be opposite over hypotenuse. The opposite being H and the hypotenuse being A. But we know that sine of theta hat is just sine of theta, using our knowledge of the reference angle and our arithmetic of the unit circle. So if and only if H is A sine theta, well, here we go again, we get the same thing. So this implies, just like we had before, the area, same calculation, I won't write it again, will just be 1/2 base times height, which is just 1/2 AB sine theta. So what we're seeing here is that even for, I mean, when you prove this, I mean, we're thinking we just have to look at the 4 quadrants, or if we're looking at triangles, it as an area calculation, we kind of need to verify it for acute and obtuse, because those are the types of triangles that we would be seeing in this class. So this kind of gives us the full spectrum here. So this formula here is very user friendly, but the fact is that we don't, this is the proof here. So when we do the actual area calculation, we just use our theta here because we have this equivalence from the reference number or reference angle, which they're computed to be the same. So all of this arithmetic that we've been doing, we still do now. So you can't get away from that, unfortunately. Now, here's something I want to show you. because this is going to help us segue into the inverse trig functions again. But I want to now use what we know about right triangles to make some computations. So when we finish this particular section, I'll do some just some simple examples with maybe some triangle area and sector area, see how they combine. But now this example, so now that we can do areas, when you do your WebAssign, if they ask for an approximation, give it. Otherwise, you write an exact answer. Don't approximate unless you're directed to do so. So here's an example that's just like we had in chapter 5. So we have cosine theta equals 5 over 11. And so you're thinking Pythagorean identities are basically the Pythagorean theorem. We're given that sine of theta is less than 0. Okay, so let's look at this. Cosine is positive, sine is negative. That is, x is positive, y is negative. So that puts us in the fourth quadrant. So that's obvious. So theta is in the fourth quadrant. So what we see is x is positive, y is negative. Now we're good. This is so simple now with the triangles that maybe you'll do a happy dance with this. I don't know, maybe you're thinking, well, okay, Professor Ron, I'm not that happy, but I see what you're saying. So now notice cosine theta is 5 over 11, but this is just x over r. Again, we think of the triangle adjacent over hypotenuse. So if you want, you can just think of it like this. R, X, Y, just a simple right triangle. So now this if and only if we can just take the ratios directly. So we have X equals 5, R equals 11. So this implies we use Pythagorean theorem. So y squared equals 11 squared minus 5 squared. So I guess we can use our handy dandy difference of squares just to get practice with it. 11 minus 5 times 11 plus 5. So that's going to be, in this particular case, that's going to give us what? A 6. And this gives us a 16. So we've got what, 2 times 3 and a 4 times 4. So let's see. So we've got 2 times 3, 4 times 4. So that's good. That's just going to be a perfect square. So that's good. So select, what is it? Y is negative. So select negative. So y equals the negative square root of 2 times 3 times 4 squared. So this will just be negative 4 times the square root of 6. So I looked at factors so we could see where the perfect square of 4 squared is. So we extract the 4. So now we've got y here. I'll just put it y again. So we're done. So now compute. Let me write what we do. You know we're going to do compute remaining trig functions. So when you look at this, you're thinking, okay, well, we're good to go. So we've got cosine is 5 over 11. So secant, let's do the easy ones. Secant theta will be the reciprocal, 11 over 5. So you're thinking, is this any different from what we did before? No, we're just kind of looking at it in terms of ratios, which kind of change it up a little bit, but it's still Pythagorean. You may find this easier, and if you do, good. I mean, we're just doing ratios now, so we're good to go. So secant theta is 11 over 5, and then sine theta, that's going to be what? Y over R, opposite over hypotenuse. So that's -4 root 6 over 11. So we're thinking in this particular case that we keep hinging on the reciprocal nature. So we'll cheat again. Cosecant theta will be the reciprocal of this. So that'll be -11 over 4 root 6. No need to rationalize. And so we got secant, sine, cosecant, and then tangent theta. That'll just be y over x. So y is right here, -4 square root 6 over x, which is 5. So it's kind of simple, I guess, when you think about it, thinking about ratios. So this has improved our ability to compute. And then cotangent theta would just be the reciprocal of this, -5 4 root 6. So examples like this, even though they're dry and boring, they really do kind of highlight the new abilities we have. That is, now if we think in terms of ratios, the arithmetic is all the same, no change there. When we do algebraic expressions of sine and cosine, you did them just like we did in chapter 5. There's no difference. Reference angle, reference number, no difference. So we're not getting a pass on all the other arithmetic that you didn't like in chapter 5. We're just getting a new way to kind of look at things that may actually give us a little bit more enlightenment into the situation. So now, like we have before, we've got these imposed triangles. So now when you think of the unit circle, you really can look at these triangles and add that to the mix. I mean, that's what we didn't put in before. But we see with the law of similar triangles that it doesn't matter how we interpret the sine or cosine. If we're thinking of a reference number or, for instance, a distance on the unit circle or the abstract concept of an angle, it's all the same. Laws of similar triangles kind of brings the two interpretations together. So now let's look at a couple of examples. We'll just end with this. Here's a neat example. For instance, you should be able to figure out the area of an equilateral triangle. You can use what I did at the beginning of the lecture. So I'm just going to give this, and I want you to verify this. Verify this. That if you have an equilateral triangle of side S, that's how we start. This implies that the area will now be the square root of 3 S squared over 4. You need to prove that or verify that. You should be able to do that quickly because that's just a 60 degrees, 60 degrees, 60 degree, and you can chop it up to make 30, 60, 90, and this will fall right out. So verify that. You should commit that to memory. That's something you use in calculus. You should know that. Now, for the last thing that we want to do, we want to put the triangle area problem together with the circle, sector area. So let's draw a circle. And then we'll rediscover our inverse trig functions, which I'm sure you enjoy. Those are fun, right? All those nice identities. So we got a circle here, got a central angle of 120 degrees. So we have a central angle of 120 degrees. We have a radius of 6, and we draw a chord connecting these two terminal points right here. And we have this, in this case, the blue, the shaded area. So here's what we want you to do. Here's what WebAssign asks you to do. It says compute area, or compute the area of the shaded portion. Compute area of shaded portion. So we think, okay, well, that's just going to be the area of the sector minus the area of the triangle. So this implies area equals sector area. That's what we learned about last time, minus triangle area. Now, if you like, we can go ahead and do a computation here. We can convert this to radian measure if you want, just to make it simple. And we'll do that in the calculation because we know we need that for sector area. So this will be 1/2 r squared. So we get 6 squared times theta. So this will be 120 degrees times, well, we don't leave the degrees out when we do the computations. We're fine with that. We're doing the conversion. So degrees are pure numbers too. It's just that we remind ourselves because radians are pure numbers, but we don't write R, okay? So, because we're lazy. So we have pi over 180. That converts the degrees to radians. Pure number to pure number, right? Okay, then minus the triangle area. So this will be 1/2. So again, we have AB sine of this. So AB, that's going to be, again, be 6 squared. And then we have sine of 120 degrees, or we can just go ahead and convert it, 120 degrees, pi 180. Okay, so when you look at this problem, half the stuff's the same. It's kind of like doing the Alonzo's tethered cow, you know, with the cow grazing and can run all over the place, just doing a bunch of sectors with angles of pi over 2. It's a similar kind of problem, but probably about the same level of difficulty. So now we get what 1/2 times 6 times 6, that's common to both. And then of course, this will just give us a 2 over 3. So this is 2 pi over 3. And now of course we have sine of 2 pi over 3. So we'll use our radian, we'll use our, again, our unit circle, or use the reference number or reference angle. So this will be what, 3, 2 into 6 is 3, 3 times 6, 2 pi over 3. And so again, this is in the second quadrant. So it's just like we did the last proof. So this will be the same as sine of pi minus 2 pi over 3 using the reference. So we have 18, 2 pi over 3 minus sine of pi over 3. So that's our friend in the first quadrant, and that's square root of 3 over 2. So we have 18 times 2 pi over 3 minus square root 3 over 2. Now, of course, we can get a common denominator of 6. So this will be a 4 pi, and then it'll be minus 3 root 3. So 2 into 6 is 3, 3 root 3, 2 into 6, 3 into 6 is 2, 2 times 2 is 4. So 18 over 6, that'll be 3 times 4 pi minus 3 root 3. And that's your exact answer. Now, of course, if WebAssign wants an approximation, you can do that. It doesn't matter if you know how to use your Google calculator, but these are really nifty little geometric problems that now we can use because we now are starting to interpret trigonometry in a dual way. That is, they really do complement each other, but they focus on different types of techniques. So again, when we think about the area of the triangle, we were able to deduce that using our new interpretation of sine of an angle as opposite over hypotenuse. Again, everything that we have now, the theta, the angle measure, is taking the rho over the rho of the t of the measure, the t measurement along the unit circle. So we start with measurement along the unit circle, then we abstract to the abstraction of an angle, which corresponds to the measurement on the unit circle, and then rig another version of trigonometry, which has all the same rules. The only additional part is that now with these triangles, we have these nice ratios, which are really just the Pythagorean identities that just kind of get stuck into the mix. So everything is pretty much the same. We just now have the luxury of having triangles to do computations. So what we'll do on the next class, ladies and gentlemen, is we will continue with this concept and talk about our inverse trig functions, how those relate with the triangle, see how that works, and then look into some triangle theorems. The triangle theorems are a little bit dry, but at least they give you a way to look at the geometry in a new light. The main focus will be on the identities in chapter 7 and solving equations. And I will actually allude to solving some equations next class. That will be extremely important to what we do in the future. So have a great day. Take care of yourselves. Thank you for your attendance this morning. And if I don't see you at office hours, we'll see you bright and early on Thursday morning. Bye, everyone.
Have a good day, sir.
Thanks, you too. Thank you.